You are standing in a walled courtyard in northern China, and the temperature has just dropped to 15 degrees below 0 Fahrenheit. The wind coming off the Siberian steppe hits exposed skin like a blade, and it can freeze bare flesh in minutes. Step through a wooden doorway behind you, and the air turns still. The room holds a steady 65 degrees. No electric heater is running, no furnace is humming in a basement. There is only mud, fired brick, and paper soaked in oil. For over 2,000 years, families across northern China beat this exact cold using geometry, waste heat, and airflow. It all started with a wall built to fight the wind itself. Long before any bricklayer stacked a single brick, ancient builders had to answer one brutal question. How do you stop a wind that can freeze skin in minutes? Every winter, a massive dome of cold air called the Siberian High builds up over Central Asia. It pushes south like a slow-moving flood, sending gale-force polar winds straight across the open plains of northern China. Few natural barriers stand in its path across the exposed North China Plain and the Low S Plateau. A poorly built home in this environment does not just feel cold, it loses its heat completely within hours, leaving occupants exposed to the same temperatures as the world outside their own walls. Ancient masons solved this with a single, deliberate design choice. They built the rear wall of the house, the one facing due north, as a solid slab of masonry with 0 windows. A snowplow blade bolted to the back of a truck works the same way. It does not stop the wind by matching its force. It stands there, thick and heavy, and lets the wind slide up and over it. Here is the physics behind that wall. Builders constructed it between 1.5 feet and just over 3 feet thick, using 2 outer layers of dense, kiln-fired grey brick, sandwiching a core of packed low-S soil, gravel and straw. Low-S is a fine, wind-blown silt that behaves almost like a battery for heat, absorbing and releasing thermal energy slowly. So a mass of packed low-S resists rapid temperature swings far better than a thin wall ever could. With 0 window openings on this face, there was no path for warm indoor air to escape, and no path for freezing outdoor air to sneak in. The wind hit that flat, heavy surface, lost its speed against the mass, and rolled upward over the roofline instead of punching through to the family inside. This wall blocked the wind completely. Blocking the wind adds no warmth to a freezing room though, and every single day the sun rose over that same courtyard, carrying free energy that most builders were wasting entirely. Blocking the wind kept the cold air out, but ancient builders still faced an empty, cold room with limited fuel to spare. Wood was scarce in many regions. Coal was expensive. If a family wanted warmth during the day, they had exactly one free source available to them, and it was hanging directly overhead. The challenge was capturing that sunlight efficiently, because the winter sun in northern China does not sit high in the sky. At a location like Beijing, which sits near the 40th parallel, the winter sun only climbs to about 26 degrees above the horizon at high noon. That is a shallow, low angle, almost like a flashlight beam skimming sideways across a table instead of shining straight down onto it. Builders turned the entire courtyard into a tool for catching that shallow light. The courtyard itself formed a shallow bowl carved between 4 buildings. The main house sat on the north side, facing south, with large windows lining its front wall. Architects calculated the exact width of the courtyard and the exact height of the surrounding roofs so that low winter sunlight could travel clear across the open yard and strike those south-facing windows directly, warming the interior brick and floors. In summer, the sun climbs to a much steeper angle, around 73 degrees overhead. At that steep angle, the wide overhanging eaves of the roof throw a long shadow across the same windows, blocking the harsh summer sun before it ever reaches the glass. One fixed piece of architecture, the roof eave, acted as an automatic seasonal switch. It let low winter light in and kept high summer light out, without a single moving part. This is why ancient builders insisted that main rooms always face south. It was applied solar math calculated by hand, centuries before anyone owned a protractor rated for architecture. Sunlight poured into the house every clear winter day, warming the brick floors and the mud walls of the main room. The moment that sun dropped below the horizon, though, all of that borrowed heat began radiating right back out into the freezing night, and builders needed a second system to keep the warmth going after dark. Trapping daylight solved half the problem. Northern China's winter nights stretched long, and temperatures outside kept falling long after sunset. An open fireplace seems like the obvious answer, except across the centuries, that option became increasingly hard to sustain. Rapid population growth, city building and farming steadily thinned the forests across northern China. What began as a manageable timber supply under the Han and Tang dynasties turned into a severe fuel shortage by the Song, Ming and Qing dynasties. Wood grew scarce and expensive, and what little remained was reserved for construction. Ordinary families turned to agricultural leftovers, things like dried corn stalks, dead leaves, twigs, and low-grade coal. These fuels burn fast and hot for a short time, then die out almost immediately. An open fireplace fed by this kind of fuel would flare up, lose most of its heat straight up the chimney, and leave the room cold again within the hour. Builders needed a completely different strategy. Heating the open air of a room is like trying to warm an entire swimming pool with a single hot stone. Instead, they decided to heat a solid object that occupants could sit directly on top of. That object was the Kang, a raised, hollow platform built from mud brick and clay tile, connected directly to the household cooking stove. The Kang worked at the scale of an entire piece of furniture fed by smoke instead of direct fire. Every single time a family cooked breakfast or dinner, the leftover hot exhaust from that stove did not just vanish up a chimney, it got redirected sideways into a hidden network running underneath the family's own bed platform. Routing that hot exhaust directly under a place where people sleep raised an immediate and dangerous new question. How do you keep a bed warm for half the night without turning it into an oven? A platform that gets too hot will burn the people sleeping on it. A platform that gets too cold defeats the entire purpose. Ancient masons had to hit an incredibly narrow temperature window, and they did it using brick geometry and the physical properties of clay. The Kang was built as a hollow box of mud brick, clay tile, and lime mortar, occupying anywhere from 30 to 50% of the floor space in the main living room. Inside that hollow box, builders carved a maze of narrow channels, laid out in winding, snake-like patterns or simple grids, similar to the way a car radiator forces coolant through dozens of thin tubes to maximize contact with outside air. Here is the physics in motion. Hot exhaust gas leaves the cooking stove at somewhere between 200 and 400 degrees Fahrenheit. As that gas travels through the long maze of brick channels, it sheds heat with every foot of distance, and by the time it reaches the far end of the Kang, it has cooled down to somewhere between 120 and 180 degrees Fahrenheit. Along the way, the surrounding clay and mud brick slowly absorb that heat and store it as thermal mass, the same way a sun-warmed sidewalk holds its heat long after the sun goes down. By the time that heat has fully transferred into the brick mass, the surface temperature of the Kang platform settles into a stable range of roughly 77 to 86 degrees Fahrenheit. Warm enough to sit on comfortably, never hot enough to burn skin, and never hot enough to crack the clay tiles above it. Because that thick brick mass releases its heat slowly, the Kang kept radiating warmth upward for 8 to 12 hours straight, long after the cooking fire had gone completely cold. A family cooking 2 meals a day, morning and evening, could keep that platform warm around the clock, using fuel they were already burning anyway to make dinner. This was one of the most efficient heating systems ever built by hand. Routing hot smoke through a maze of brick channels directly underneath a family's sleeping platform created a silent, invisible danger that could kill an entire household without warning. A single crack in the wrong wall could fill a bedroom with invisible, odorless gas, while an entire family slept just inches above it. This was the real cost of the Kang system if it was built even slightly wrong, and ancient masons knew it. Preventing this disaster required understanding one basic law of moving air. Hot air rises, and it rises faster when it has a tall, narrow path pulling it upward. Builders placed the stove's combustion chamber at the lowest point in the system, then ran a tall exhaust chimney straight up above the roofline, sometimes rising several feet higher than the peak of the house itself. A drinking straw stuck into a warm drink on a cold day shows the same effect at work. The air inside that straw heats up, becomes lighter than the air around it, and rises straight out the top on its own, pulling more air in behind it as it goes. Builders relied on this same principle, called the stack effect. The tall chimney created a continuous suction, pulling hot gas upward and outward through the flue channels, which kept the pressure inside those brick tunnels lower than the pressure inside the living room. With lower pressure inside the flue than inside the house, smoke and gas could not leak sideways into the bedroom, even through a small gap, because air always flows from high pressure toward low pressure. Builders backed this up with a second defence at the material level. Clay mortar sealing the flue joints was mixed with chopped rice straw, animal hair, and pig bristle. These fibres acted like the rebar inside modern concrete, gripping the clay matrix and stopping it from cracking apart every time the brick heated up and cooled back down. Fibre reinforcement kept the clay intact through repeated cycles of thermal expansion and contraction, sealing off exactly the kind of gap that could leak deadly gas into the room above. This system worked well in a single farmhouse bedroom. An emperor sitting inside a palace hall the size of a barn needed to heat far more square footage than one modest Kang platform could ever cover. Warming one small room was manageable. Warming an entire imperial hall filled with soldiers, officials, and members of the royal court demanded something built on a completely different scale, and it had to happen without a single visible flame or wisp of smoke inside the building. Palace architects took the basic idea behind the Kang and expanded it underneath the entire floor of the hall. This system was called the Dikang, and instead of heating one raised bed platform, it heated the stone slab that every single person in the room was standing on. The mechanism started outside the building entirely. Workers dug deep furnace pits, called jiaolu, into the ground beneath the exterior corridors, well outside the walls of the main hall. Servants stood outside in the cold and fed these furnaces with high-purity charcoal, keeping every spark, every ember, and every trace of smoke completely away from the emperor and his court. From those exterior furnace pits, hot exhaust gas travelled through a network of underground stone trenches running beneath the entire floor slab, exactly like ductwork running beneath a modern house, except carved directly into packed earth and lined with fired brick. As that hot gas moved through the underground trenches, the massive stone floor above it slowly absorbed and held the heat. Modern researchers running fluid dynamic simulations on one of these palace systems found that historical builders were hitting an almost perfect ratio of heated floor area to total room size, somewhere between roughly a quarter and 2/3 of the floor, without ever touching a calculator or a thermal sensor. They arrived at that number purely through generations of trial, failure, and careful observation. The floor stayed warm. The air stayed smoke-free. But even with a perfectly heated stone floor beneath their boots, every single person walking through the palace still had to pass through a doorway. And one open door in freezing weather could undo hours of careful heating in a matter of seconds. A heated floor means nothing if a single gust of wind through an open doorway can flush all of that warm air straight out of the building. In the coldest regions of Manchuria, where winter temperatures plunged far lower than the rest of northern China, builders faced this exact problem every single time someone walked through the front door. Their solution was a design called the pocket house, or ku dai fang. Instead of placing the main entrance in the center of the building, the way most homes were designed, builders shifted the door all the way to one far corner. Anyone entering the house first stepped into a small, screened buffer space before ever reaching the main living quarters. A submarine hatch with 2 doors instead of 1 works on the same logic. Air from outside gets trapped in that small buffer pocket first, and it never gets a direct straight line into the main room. By offsetting the entrance this way, builders created a dead zone of trapped, still air that absorbed the shock of the outside temperature before it could ever reach the family's living space. Every time the outer door opened, cold air rushed into that small pocket and stopped there, instead of blasting straight through into the heated rooms beyond it. Windows needed their own version of this same defence. Builders covered wooden lattice frames with thick mulberry paper, then soaked that paper in boiled tung oil. The oil treatment sealed the fibres of the paper together, creating a surface that blocked wind and moisture almost completely while still allowing soft daylight to pass through. Trapped air pockets inside the fibrous paper acted as a thin insulating layer, similar to how a double-pane window traps a layer of air between two sheets of glass today. Paper conducts heat far more slowly than a single pane of glass, and these oil-treated windows held indoor warmth better than the glass options available in most of the world at the time. Every one of these systems, the solid wall, the courtyard trap, the Kang, the Dikang, and the pocket house entrance, now worked together as one connected machine. That machine was about to face its ultimate test, spanning not one brutal winter, but centuries of falling global temperatures. Between the 14th and 19th centuries, the entire planet cooled during a period historians call the Little Ice Age. Winters across northern China grew even harsher than before. Crop seasons shortened, and the margin for error inside every household shrank dramatically. This was the ultimate stress test for every piece of engineering already built into the courtyard house. A single weak wall, a single cracked flue joint, or a single poorly sealed window could mean the difference between a family surviving the season and a family freezing in their own home. Builders responded by refining every system already in place. Wall thickness increased. Brick kilns improved, producing denser, less porous grey brick that resisted the freeze-thaw cracking that plagued lower-quality masonry. Standardized building manuals, written by court officials, spread these refined techniques to builders across the empire, ensuring that a farmhouse 300 miles from the capital used the same proven flue geometry as a palace hall in Beijing. The proof of this system's success sits in the numbers themselves. As recently as the early 2000s, field surveys counted roughly 175 million people across rural northern China still relying on Kang platforms for winter heat, using a design that had barely changed in over 1,000 years. Rome's underfloor heating system, the Hypocaust, required massive amounts of dedicated timber fuel and collapsed the moment central Roman infrastructure fell apart. The Chinese system required no extra fuel at all. It simply recycled the heat of a family cooking dinner using basic mud, brick and straw that any household could maintain for generations. That is the real engineering lesson buried inside this courtyard house. Ancient builders studied wind pressure, solar angles, thermal mass and airflow, then built a house that worked with those forces instead of fighting them. A wall deflected wind. A courtyard caught sunlight. A bed platform recycled cooking exhaust before it disappeared up a chimney. Every single piece did double duty, and together those pieces kept millions of families warm through the harshest winters recorded in human history, using earth, fire and physics.